And let me extend that welcome message to all of you who are watching this talk, and thank you very much for being here, and good morning to you all. And I'm going to talk to you about how you can supercharge your JavaScript with WebAssembly. So we're going to take a look at, how WebAssembly works. I'm going to go through a couple of slides that I've prepared, and I'm going to jump into a couple of demos, and I prepared 4, but we'll see how much time I have left to show those to you. So that's me. So my name is Tamas. I work as a developer experience engineer at a company called Cloudinary, and you can learn an awful lot more about me on my personal website, which you see on the top of this slide, which is tpiros.dev. So let me take you back in time to about 2018, and let's take a look at the web platform as it was back in the day. And please bear in mind that this is an overly simplified view of the web platform. So you have your browser. The browser contains, a number of web APIs, such as the Fetch API, for example, and some others. And there's also this virtual machine as part of your browser, which is capable of compiling, interpreting, and executing your JavaScript code. So this is how the web looked like back in 2018, from a browser's perspective, overly simplified, of course. Now, the web, as we know it, is progressing at an incredible rate. So just in the past couple of years, we've seen a lot of new frameworks and a lot of new exciting developments in place. And JavaScript has become the predominant programming language that we use on the web, but it has some limitations, right? There are some scenarios where you just can't use JavaScript to achieve something. And even if you can, you may hit a performance bottleneck, or you may introduce some performance issues in your application. So in that sense, JavaScript certainly has some limits. And it's especially difficult to use JavaScript to achieve low-level tasks, right? So when you want to do something really low-level, some CPU-intensive processing, maybe, you can do it with workers, but it's going to get, overly complex and more complex as you kind of find yourself falling into various rabbit holes, which I have done many, many times. Let me assure you that. So, what can you do? What options do you have if you want to do some low-level processing, or you want to do some performance processing happening inside your web application? And this is where we need to talk about this thing called WebAssembly. And WebAssembly was created back in 2015, but I have a slide, note here. There was this other thing called Asm.js, which does actually predate WebAssembly by 2 years. And I think Asm.js was a sort of it's not necessarily a product, but a library that the Mozilla research people have created. And that library, this Asm.js library, allowed developers to bring applications written in a language such as C and run those as web applications. And that is exactly what WebAssembly allows us to do. So since 2019, WebAssembly is part of the official W3C recommendation list. So that means that the W3C takes care of the spec for HTML, they take care of the spec of the CSS, and now it's also part of the spec. WebAssembly is there. So it's as official as it can get. But what is WebAssembly? What is the official description for WebAssembly? And I kind of copy-pasted this from the MDN documentation, and I'm not going to read this out for you, but essentially, WebAssembly is a low-level programming language that allows you to take applications written in a language such as C or C++ or Rust and execute those in a web context. So I come up with my own simplified version of the definition for WebAssembly, which is pretty much, it allows you to run native apps on the web. And by native apps, I mean an app that you have written in C++ or in Rust or in Go or any of these lower level languages. So how does that work? Well, WebAssembly functions, so these functions that you have in C++ and you port those to WebAssembly, can be exposed to JavaScript. So inside JavaScript, you can actually call and consume functions from WebAssembly, and this is how this whole process comes together. But of course, there's a lot more to it, which we're going to get into the details for. Now, I would like to clarify, not necessarily a myth, but something that I've heard other developers say, and I've seen blog posts about this, where the title was, "Oh, WebAssembly is the next big thing, and then it's going to dethrone JavaScript." this couldn't be further away from the truth. So WebAssembly is not here to replace JavaScript and to dethrone JavaScript, but WebAssembly is here to enhance or to augment what JavaScript can do. These two technologies work seamlessly side by side, and because of the W3C recommendation and all the work efforts that people put into making WebAssembly much better, the seamless integration is just going to get to the next, to a whole new level. And let me just clarify this again. WebAssembly is not here to replace JavaScript. So if we take a look at our, oversimplified view of the web platform, you again have the web APIs as part of your browser. You now have, in 2021, you have newer web APIs. But most importantly, the virtual machine that you have that is capable of interpreting and compiling and executing your JavaScript code is also able to do the same with WebAssembly code. So the same engine can compile, can interpret, and can execute the WebAssembly code that you have. And this is true for all modern browsers today. So the question is, how can you actually work with WebAssembly, and how do you create WebAssembly files? And then, what does the process look like? So, as part of the web APIs, there's a relatively new API called the WebAssembly JavaScript API, which essentially allows you to load a WebAssembly module into your web application using a variety of JavaScript methods. And there's two ways of doing that. One is called the streaming method, where essentially this JavaScript API turns your WebAssembly bytecode into a module or into an instance, and then you can work with it just as you would be working as an ES 2015 module. And the other way, you can also use the fetch API to sort of fetch the WebAssembly module, but then you need to turn that bytecode into a module manually, which is also possible. There are different ways that you can achieve the same thing. You need to investigate which one is more suitable for your use case. But there's this WebAssembly JavaScript API that helps you along the way. And this is why I said that there's a seamless integration between WebAssembly and JavaScript. So how do you create a WebAssembly module, or this file with a WASM extension? And there are sort of two ways, or I put this into two silos. And one way is when you have some code written in C or C++ or any other so-called LLVM supported language. For these situations, you have a tool called Mscripton, which has a compiler called EMCC, which is the Mscripton compiler, and you just tell it where your C or C++ application is, and then you say, hey, compile me or create me a WebAssembly module, and then you basically target a WebAssembly module, and it's going to create that code for you, and then you consume that WebAssembly module using the aforementioned WebAssembly JavaScript API. Another way is that maybe you have something existing in a .NET language, in Java, in Ruby, or Go, or in other words, a non-LLVM type language. Most of these languages have compilation targets for WebAssembly. So you just, from your Go application, you say, here's my Go app, please produce a WebAssembly module from this project. You can set the flags, and then you will end up having a WebAssembly module. And then the process is going to be the same. You load and consume that using the JavaScript API. Now, there's a large number of languages that compile to WebAssembly. So .NET, C, C++, C#, PHP, Python. And there's also this thing called AssemblyScript, which is very similar to TypeScript, but I need to clarify that you can't take your TypeScript code and compile a WebAssembly module from that. You need to use AssemblyScript, which looks and feels a lot like TypeScript. And this person on GitHub has actually collected all the languages that compile to WebAssembly, so feel free to visit that URL. Now, before we take a look at the examples, what are the use cases for using WebAssembly? Well, one particular use case would be make use of existing code. Maybe you have something that you've written in C and C++ or Go, and you would like to port that to the web. That's a perfect use case for using WebAssembly. Sometimes, you want to create something that performs well. And here I have to say a clarification. When I say performance, I actually mean reliable performance. So you can achieve reliable performance with WebAssembly. And you can also have access to things like shared memory, threads. SIMD even. Sorry, I can't say these things properly. But when I say reliable performance, what I mean is that, when you create your WebAssembly code, you basically define all the data types, right? So the compiler behind the scenes doesn't need to do this, dynamic stuff that it would need to do with JavaScript. So this is what I mean, that you can achieve reliable performance when you use WebAssembly. And in some cases, there's also the size. Writing some code in JavaScript and writing the same code in WebAssembly would result in the WebAssembly binary to be much smaller, and the WebAssembly binary can be heavily compressed using, like a gzip or a broadly inside your browser. So you may benefit from size differences between your modules as well. Okay, so I'm going to switch to my demos, and I am going to show you 4 demos because we have the time for that. And I'm going to start with a very, very simple one, which is this one right here. So let's assume we have this existing C function where we have a method called inSquare. It takes a number and then we return that number squared. Now, in order for me to create a WebAssembly module, I had to execute this emcc command, which I mentioned is the mscripten compiler. It takes our C file, produces a WebAssembly, and it also produces its square.js file, which is what we would refer to as some glue code. So the glue code is what ties your WebAssembly module and your web application together. So when you run this command, you will end up having a square.js JavaScript file and a square.wasm WebAssembly module. And then I created a very simple HTML file where I am essentially importing square.js, and then I create a simple object where I have a property called calculateSquare, and this is now going to directly call the inSquare method, passing in a number as an argument and then returning a number data type. And I have in my HTML, I have an input for a number, I have a calculate button, and I have a result paragraph. So essentially, when someone clicks that button, I take that number, whatever was inputted in there, and I call the api.calculateSquare method with that number. So essentially, I'm squaring the number using WebAssembly via this application that I've written in C that is now ported to the web. Now, before you say, well, I can do the same in JavaScript, I know that, but this is the most simple example that I could come up that demonstrates how you can actually execute or how you can call a method from C inside a JavaScript environment. And we're going to take a look at this in just a moment. But another example that I want to show you is cube.go. And because I'm using Go, things are a little bit different here. So what I have is a cube method, which, as you can see, takes a number and then it multiplies it 3 times to get the cube of that number. But you notice that from my Go file, you see something very, very familiar. You see document, get element by ID, result, and then inner HTML. So what's different in terms of using mscripten and LLVM languages and something like Go is that from Go, or from the context of Go, I can directly manipulate my document object model. So this is going to calculate the cube of the number, and I'm going to set the inner HTML of the result paragraph from my context of Go. And what I'm doing in my main function for Go, so for those of you who are familiar with Go, I'm just essentially exposing the cube function. So what I do here is tell the Go compiler to target WebAssembly, and I'm going to build this cube.wasm. So that's the WebAssembly module that you see as a result of that. And then I also took this wasm_exec.js file from the Go website, which is their glue code, which, the square.js is something that we generated for Go-based applications. You need to grab this on your own. So let's take a look at the HTML version of this. So notice that here I do the instantiate streaming. I use the fetch API to fetch that module, and then I essentially start this Go runtime environment. And because I've started this Go runtime environment within my browser, I can just call the exported method and then pass in the number or the value from that number field. And then the calculation is going to happen via that WebAssembly module inside Go. And then the result from Go is going to be pushed into this paragraph with the ID of result. So if you take a look at this, here's the first example. So I add 2, I get 4, I get 3, I get 9. So this is the square function. This is now using the C method, and here's the Go version. And as you can see, everything works as expected. Now, as I said, this is not really a good use case for WebAssembly because you can do this very easily in JavaScript, but I wanted to show you in a very simple way how you can achieve this. Now I'm going to change to 2 other examples. And the first one is going to be a much larger application that I created in Go. And I'm going to show you this application. I'm going to show you another application, but I need to sort of give you a preface for this, like why are we talking about this? So I mentioned that I work for a company called Cloudinary. And the one thing that we do is image optimization, image transformation, and an image delivery. Think of it as an image CDN. You have images, you upload that to the service called Cloudinary, you get an access URL for that image, you put that access URL into your browser, and then you get access to that image. And in this case, we can take a look at the headers. So this image is 583 kilobytes. And of course, this is the access URL for that. It's a JPEG, and we can verify that that is in fact a JPEG. Now I'm going to add 2 more flags, and we're going to see if things are changing. So I'm going to add fauto and qauto to the URL. So take a look at this. I added these 2 things. Fauto is automatic format, qauto is automatic quality. So what we're doing here, we are essentially with fauto, we are taking a look at the browser where this image is being requested from. And if it's a Chrome browser, which I'm using at this moment, then Cloudinary is going to generate a WebP image, and it's going to deliver that WebP image for us. Why? Because WebP is a much better image encoding for the web, and it's going to result in a much smaller file size as well. qauto is another flag, which basically takes the image into consideration. It analyzes the image, and it's going to reduce its quality in a way that is not affecting the human eye. So it's going to do some quality reduction without introducing what we call visual artifacts. Just by adding these 2 things, notice that the size from 583 kilobytes went down to 32. And if I explore the headers, I can see that this is a WebP image. And I thought, this is great that we're doing this, but I wanted to learn a lot more about the image formats. And so I created this Go application where, for example, if Cloudinary returns a WebP image, I analyze the WebP image, and I want to know, what kind of WebP container are we talking about? Is it VP8? Is it VP8L? Does it have an alpha channel? If it's a PNG, is it interlaced? Again, what kind of PNG is it? Is it PNG 32? Is it PNG 8? So on and so forth. And I could very easily do this by using existing libraries in the context of Go. So Go has a WebP library, it has a PNG library. So I wrote a lot of code, as you can see here, to analyze these images. And then I built a WebAssembly module for this, which then allows me to do the following, where I'm going to go here and I'm going to add fauto to this particular image. And I'm using a Chrome browser. So I'm going to hit check. And this is now a JPEG. Okay, so let's see what happens if I do qauto as well. We will get a different, actually, let's do the same example that we had, which was woman.jpg. So if I check this, notice that I'm not only saying this is a WebP, this is a WebP with a VP8 container, and it is lossy and it doesn't have an alpha channel. And the information that you see here is basically returned to me from that Go application, right? And I could change the browser which, by the way, the user agent, you can change only using Chrome DevTools by selecting network conditions. And you can say, well, make the request as a Safari Mac. So now I'm making a request as a Safari Mac, and let's see what happens. Well, notice in this case, I'm not only saying I get a JPEG, but I get a JP2 or a JPEG 2000, which is a much better encoding for Safari. So this particular tool allows me to explore what is happening behind the scenes and go one level deeper. Now, the other example that I prepared is, falls into that other silo that I mentioned, which is, existing code and porting existing code to the web. So we have at Cloudinary this thing called the simulacra, which is structural similarity unveiling local and compression related artifacts. So this is a C++ application that my colleague Jon has created, back in 2017. Very simply put, I mentioned this QAuto flag, which analyzes the image and it reduces the quality in a way that is not affecting the human eye. So we're not going to introduce, pixels and other visual artifacts in the image. So what we've done at Cloudinary, we basically asked users, real, human users, to take a look at two images and tell us if the quality reduction is bothersome or the quality reduction is good. Now we took that and we took existing researches from these various people, as you can see it mentioned, and we came up with this project, which basically gives us a number where a number that is closer to 1, the more distractive the quality reduction is, and the closer that number is to 0, the better the quality reduction is, if that makes sense. So this C++ project, as you can see, is it wasn't meant for the web. In fact, it's a CLI project where you create a binary called simulacra. Parameter 1 is going to be the first image. Parameter 2 is going to be the second image. You run it, and it's going to return a number for you. So what I've done, I took this application and I created a WebAssembly module for it. And because I've done that, I can now run the same sort of functionality inside my browser. So here's, an original image, and here's an image where I'm actually saying Q_1, which is going to introduce a quality 1 version of that image. And I'm not sure how much this is coming through the stream, but this is a really ugly image, right? There's lots of pixels, colors missing, color bleeds, so on and so forth. So if I calculate the similarity for these, this is going to give me a number that is going to be close to 1, right? So it does the calculation and it's 0.4. And in our world, anything above 0.1 is considered to be bad. Now, if I do a quality 100 on the flip side, we should get exactly the same image. So there shouldn't be a quality difference in between them. So we're going to see if that's going to work, but hopefully it will. At some point, I should be getting a 0. If we're not getting a 0, then I'm not going to. There we go. So we get a 0, indicating that these images are identical, which they should be because I haven't reduced the quality. And why we have this tool? Well, we have this tool because what if I do QAuto? That does the automatic quality reduction. So I just want to verify that in fact our QAuto algorithm is correct. And as you can see, the response is 0.037, which is much lower than 0.1. So the automatic quality reduction in this case works perfectly. And the only reason why I can have this tool running on the web is because I was able to port that C++ project that I have, or that we have at our company, using Mscripton, using a lot of research. I was able to port that to WebAssembly, and now I can very easily run this application in here. Now, let me just show you a couple of interesting things from the code, because I found that to be very, very intriguing. And that is the fact that I can actually access the virtual file system. So WebAssembly can actually work with a virtual file system. So what I'm doing here, I'm actually grabbing the images. I create a uint8 array from those images, and then I write those two images to this virtual file system, and then I call the calculation method, which is then, of course, going to give me the final simulacra score. So this is also very interesting, right? The amount of things that I can access and I can do with WebAssembly opens up a whole new lot of space in terms of what web developers can do and how deep and how complex the applications can go. We couldn't be able, we wouldn't be able to do this using just JavaScript, or maybe I could have done this in JavaScript, but I would have to think about how to recreate all this complex logic, which, by the way, is very computing intensive, right? Because there's lots of bits and calculations that we need to do and comparisons that we need to do, right? We need to essentially take images apart and then compare those pixel by pixel, etc., etc. And there's lots of logic in here. In fact, you see this couple of, hundreds of lines of mathematical calculations. Recreating this in JavaScript, I'm not even sure if at the first place it could have been possible, but even if it could have been possible, I'm sure it wouldn't be as performant as just bringing this C++ project to a WebAssembly module and then consuming that in this way, using the various WebAssembly JavaScript APIs and then just JavaScript itself within the browser. Okay, so I'm going to leave you with some resources. So links to mscriptum, which is the compiler from C, C++, etc., to WebAssembly. Some additional resources that you can take a look at. Someone actually ported Doom. So they compiled the game Doom to WebAssembly module, and now you can play that and run it in your browser. Someone did the same with Super Mario. There's also Squoosh.app, which is one of the flagship applications from Google that allows you to do image optimization within your browser. They also heavily rely on WebAssembly for doing all the image optimization within your browser, because otherwise it would be really, really slow. And they also have some case studies written, and they keep on updating those because they keep on expanding this application, and then they tap into WebAssembly, and then they write blog posts or make YouTube videos about it. So it's a very good project to follow as well. And then just recently, in fact, yesterday was the day when I finally managed to finish up that blog post where I explain the entire process of bringing that Simulacra C++ project to the web using WebAssembly, right? So if you want to replicate what I've done, or you just want to have a read, then that blog post is now live, so you can take a look at that as well. And with that, muchas gracias and muchas gracias, and thank you very much for attending this talk. I hope you enjoyed it, and I'm going to stick around for a little while for questions. If you have a question later on or you just want to have a chat, feel free to visit my website. You will find all sorts of links and ways to contact me. I'll be more than happy to have a discussion with you. And with that, thank you again and enjoy the rest of the conference.